Here's the cubic equation x cube plus 4x square minus 10 is equal to 0. We want a value of x that makes it 0. There's a classic trick. Rearrange it into the form x is equal to g of x, then just iterate. Rearrange it one way, like x is equal to square root of 10 by 4 plus x, and it converges in about 10 steps. Rearrange the very same equation a different way, and it explodes past 100 million. Same equation, same root. The only thing that changed was how we rewrote it, and that changed everything. Welcome back to Numerical Methods episode 2. Fixed point iteration, the method behind the methods. So what exactly is a fixed point? A fixed point of g is a value p where g of p is equal to p. In plain words, a point that function leaves unchanged. The input equals the output. Picture it. A fixed point is where the curve y is equal to g of x crosses the diagonal line y is equal to x. At that crossing, the input and the output are the very same number. That is exactly what g of p is equal to p means. Here's the move that powers everything. Rewrite f of x is equal to 0 as x is equal to g of x. Then the method couldn't be simpler. Guess a value, apply g, and repeat. Formally, xn plus 1 is equal to g of xn. Each output gets fed back in as the next input. Keep this in mind. Several methods you already know are secretly this idea in disguise. Let's see it geometrically with the cobweb diagram. Plot y is equal to g of x and the diagonal line y is equal to x. Then bounce between the two. The blue curve is y is equal to g of x and the dashed line is y is equal to x. Where the blue curve meets the diagonal is the fixed point P. It's the one place G leaves its input completely unchanged. Start anywhere, say x0 is equal to 1.5 and drop to the curve. Now bounce up to the curve to apply G, across to the line to set your next x, and repeat. Watch it spiral inward, homing in on the fixed point. This G converges. Now test a steeper G, one whose slope is bigger than 1. Same setup, the curve, the diagonal and their crossing point. Start close to the fixed point this time. But now it staircases outward and escapes. Same idea but opposite fate. The difference between spiraling in and flying out is just one thing, the slope of G. Let's pin that down precisely. What separated the two cobwebs was the slope of G at the fixed point. Here's the condition. The iteration converges when the size of G prime of P is less than 1. As long as you start near enough, it converges. If the absolute value of G prime of P is greater than 1, and it diverges. More formally, if G is continuous on an interval, maps that interval into itself and its slope stays below 1 in size throughout, then G has a unique fixed point there, and the iteration converges to it from any start in the interval. Here's the algorithm from start to finish. Pick a start, apply G, and repeat until it settles. Rewrite f of x is equal to 0 as x is equal to g of x. In step 2, pick a starting guess x0. Compute the next iterate in step 3. Xn plus 1 is equal to g of xn. Check whether the size of xn plus 1 minus xn is small enough, and if not, repeat from step 3. The whole cost is one function evaluation per step, and that's it. And notice no derivative is required, just g itself. That's what makes it so general. We have stated the algorithm. Now let's actually run it on our cubic. Use the rewrite that worked. G of x is equal to square root of 10 over 4 plus x. Start at x0 is equal to 1.5. Step 1. Put 1.5 into g. 4 plus 1.5 is 5.5. 10 over 5.5 is 1.8181818. Take the square root. X1 is equal to 1.3483997. In step 2, feed that answer straight back in. 4 plus that is 5.3483997. 10 over it is 1.8697181. Square root again. x2 is equal to 1.3673764, already close to the root. Keep going and track the error. How far each xn sits from the true root. Here's the table. Step by step the error collapses. About 0.13, then 0.017, then 0.002 and so on. By step 8, we are within 9 billionths of the root. Now look closely at those errors. Each one is about 0.127 times the one before it. And 0.127 is exactly the size of g prime of p, the slope we computed earlier. The rate isn't a coincidence, it is the slope. That's about one correct digit every step, exactly what the slope predicted. Back to our cubic x cube plus 4x square minus 10 is equal to 0, whose root is about 1.3652300. Watch what 5 different rewrites do. Rewrite 1 blows up, its slope is 15.5. Rewrite 2 breaks down, taking the root of a negative. Rewrite 3 converges but slowly, slope about 0.51. Rewrite 4 converges nicely, slope is 0.13. And rewrite 5 nails it in 4 steps, slope essentially 0. Look at that. The equation never changed, only the rearrangement did. And the slope column on the right predicts every single outcome. So here's the key insight, the one to remember. Convergence isn't about the equation, it's about the slope of g at the fixed point. Line the four slopes up, 15.5 diverges, 0.51 is slow, 0.13 is fast, and 0 is instant. The line in the sand is absolute g prime of p is equal to 1. Below it you win, above it you lose. How fast does it converge? Let's make that precise. First, the error En is how far xn sits from the true value p. We say the method has order alpha with constant c if the error obey this limit. Alpha is equal to 1 is linear convergence, alpha is equal to 2 is quadratic, dramatically faster. Where does the rate come from? Expand g around the fixed point. Two facts to start. Each step applies g and p is the fixed point. So g of p is equal to p. The Taylor expansion of g of xn about p reads as follows. Now subtract p from both sides. On the left, g of xn minus p is just en plus 1 and xn minus p is en. This one relation contains the whole story. Everything now depends on g prime p. Case 1. G prime of p is not 0. Then the first term dominates the tiny en squared term. So en plus 1 is approximately g prime of p times en. That's order 1, linear, with rate the size of g prime of p. And we already watched this happen. In the worked example, the error ratio settles to 0.127, exactly the size of g prime of p. Case 2 is the interesting one. What if g prime of p equals 0? The linear term vanishes outright. The landing survivor is the en squared term. The error squares each step. The number of correct digits roughly doubles. That's quadratic convergence. Remember rewrite 5, the one with slope exactly 0. That was Newton's method in disguise, and this is precisely why it was so fast. Now, when does fixed point iteration fail? Choosing g is an art, and there are two ways it goes wrong. First, the slope is too steep. Absolute g prime of p at least 1. Rewrite 1 had slope 15.5 and its iterates raced away. 1.5, then point minus zero point 0.9, then 6.7, then minus 470, then 100 million. Second, g leaves its domain. Rewrite 2 hit a negative under the square root. So g became undefined and the iteration just stopped. The moral is, a good g is one whose slope at p is small. Finding it is the real skill. Exercise 1. Solve cosine of x is equal to x by fixed point iteration. Take g of x is equal to cosine of x, starting at x naught is equal to 1. Does it converge, and to what? Pause here and run a few iterations yourself. Here it is, starting from 1, the values bounce around 0.54, 0.86, 0.65, 0.79, 0.70, 0.76, slowly closing in. It converges to the dotty number, about 0.7390851. The slope there is the size of sine of p, about 0.67, under 1. So yes, it converges, but just slowly. Exercise 2. The equation x square minus 2 is equal to 0 can be written as x is equal to 2 by x. Iterate g of x from x naught is equal to 1.5. What happens? Pause and try it. Watch 1.5 goes to 1.333, which goes back to 1.5, then 1.333 again, forever. It oscillates and never settles. Why? At p is equal to square root of 2, g prime of x is equal to minus 2 over square x square. So absolute of g prime of p equals exactly 1, the boundary case, neither converging nor diverging. Exercise 3. For our cubic, the rewrite g4 converged. Given absolute of g4 prime of p is 0.13, estimate how many correct digits you gain per iteration. Here's the hint. Digits per step is about log base 10 of 1 over absolute of g prime of p. Pause and work it out. Plug in log base 10 of 1 over 0.13 is log base 10 of about 7.7, which is roughly 0.89. So you gain about one correct digit every iteration. And that matches what we saw. About 10 steps for 9 digits. And that's the fixed point iteration. Thanks for watching. Three takeaways. Rewrite f of x is equal to 0 as x is equal to g of x and iterate. It converges when g prime of p is below 1 and smaller means faster. And the choice of rewrite decides everything. The equation never changed. The slope decided everything. Next episode, Newton-Raphson. When using the slope turns steady convergence into something lightning fast. Like and subscribe for more, and drop any questions in the comments.